So, good evening, everyone. I'm Calvin Joseph, and today I'll conduct your Week 10 problem solving and doubt clearing session for the course Control and Tuning Methods in Switchmode Power Converters. And we will be looking into the following. We'll be looking into what is sliding mode control, what is time optimal control for the two cases, that is, load step up time optimal control with reference change time optimal control. Okay, we will also solve some questions. So, today is the week 10. Okay. So, we have discussed what is the phase plane. If you would have remembered, that is, we have an x1 axis and x2 axis. These are your states, right? And we have seen like what different types of equilibrium points. Does anyone remember what are the different types of equilibrium points which we have?
Stable node, unstable node,
Okay.
saddle point, then stable focus and unstable focus.
Yes, correct. So there are 5 types of equilibrium points. Okay. So we had seen like it could come like this over here, could come in a straight line like this, or it could come like this depending on the eigenvalue, or it could go off to infinity also, right? Or through some point it would come here, but through another point it could go out. Like that, different fields are there, different conditions are there. So what was the reason behind understanding these phase plane, etc., was so that you can apply it for these switch mode power converters. So you have your switch mode power converters, SMPC. So where we have our x dot is equal to some AQX plus BQVN. Okay. As we have discussed earlier, it is discontinuous and everything. So what we want to do is we understand that the vector field is discontinuous. That is, when Q is equal to 1, you have x dot is equal to A1x plus B1V in, and when Q equal to 0, you have your x dot x equal to A0x plus B0V in. Okay. So what will be the equilibrium points for both cases, both modes Q equal to 1 and Q equal to 0? That is, what will be XE1 and what will be XE0?
Minus A1 inverse into
Okay. This
B1
minus
V.
A1 inverse B1 B. And this is minus A2 A0 inverse B0 Vn. Okay. So let me give some examples regarding this. So in this week, we will limit our discussion to buck converter, because that is what Sir has considered for the time optimal control and for the reference step control. Sir has considered buck converter, so we will work with the buck converter. Okay. So we have the buck converter, right? Where we have our input voltage like this. Input is over here. Sorry. You have this switch here, Q here, Q bar here. Then you have your L, you have your C, and you have your R. Okay. In this week, like we are neglecting the parasitics because we just want to get a understanding of how the behavior looks. Later on with parasitics, the behavior will be altered slightly. But for this week, to simplify it, we are ignoring it. So you have your inductor. This is your inductor current. This is your capacitor voltage. Okay. So let us construct what will be your L dIL by dt. What will this equation be? So this is your switch node. This is your output voltage node, right? So what is your L dIL dt?
When Q is 1, it is V in minus V0.
Hmm.
Q is 0, it is minus V0.
Okay, so we will write it as Q into Vn minus V0. Hmm. This is a simple notation. Here your Q1, Q0 both come into picture. Okay. Next, we will consider C into dV0 dt. That is what C dV0 into dt. So C dV0 dt is this. So, okay. Think today it's a bit unlucky for me. So then we have to draw again. So again, we have a buck converter. So you have your input over here, your Q signal here, Q bar here. So this is Q bar. You have your inductor, capacitor, load resistor R. This is your L. This is your IL. This is your VC. As you have told, so your L DIL dt, that is equal to Q into Vn minus V0 or VC. So because if Q equal to 1, this voltage over here, that is your switch node voltage VSW, is Vn. But if Q equal to 0, your voltage will be 0. Okay, so that's why LDIL dt is equal to Q Vn minus V0 VC. And similarly, your C dVC dt, that is, this is your current through your capacitor, that is equal to IL minus this I0, and I0 is VC by R. So it is equal to IL minus VC by R. Any queries in this till now? Okay, this is a simple buck converter. So now, let us draw. So buck converter has two stages. One, when you have your input over here, you have your input here, and this switch is closed, this switch is open, this is your L, this is your C, and then this is your R. Okay, your IL, your VC. So this is a condition when Q equal to 1. So can you tell me what will be your IL steady state and what will be your VC steady state? Where will they finally settle when Q equal to 1?
IL will be V0 by R.
V0 by R, okay. And VC? No, Parvati, you were saying something? So, where do you think it will settle? Joshi also? VC, where it will settle?
D into Vn.
One minute, one minute. Okay, you're saying it will be V0. Joshi is saying V0. You're saying D into Vn. Okay. So this is, you're saying V0 and you're saying D into Vn. Now, I want you to not look at it in that perspective. I want you to tell me if it is on for infinite time, almost till infinity. That is, your switch Q is closed. Q equal to 1 will always be closed. Q equal to 0 will always be open. Then where will they settle? Where will your ILs, SS steady state become? And what will your capacitor voltage become in steady state? That's it.
Capacitor will charge to Vn.
Okay, good. I think I didn't tell the question properly. Next. And what will happen to the inductor current? Would it be 0?
It will be Vn by R.
Okay. It will be Vn by R. Right? Now, so these are your equilibrium points. So your XE when Q equal to 1, that is your IL steady state and VC steady state, right? And that is equal to your Vn upon R and Vn. Hmm. These are your equilibrium points for your states when Q equal to 1. Okay? Any queries? Joshi, Parvati, Arun? Okay. So how you like how I'm looking at this is I consider that it is a DC circuit. For DC circuit means what will happen? Your inductor is shorted, your capacitor is open. So that means this voltage will become equal to Vn, right? And your inductor current IL will be equal to Vn by R. That is how you can find the equilibrium point fast and quickly. So this is for the buck converter when Q equal to 1. Now let us see for the next case when Q equal to 0. So now this is your V in and it is open over here. And this switch is closed. This is your L, this is your C, and this is your R. Okay. Now you tell me what will be the steady state values, steady state equilibrium points of these. What do you think will happen?
Sir, I didn't hear. Is it the equilibrium point for Q equal to 0 that you are
Yes,
asking?
yes, 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 yes. For Q equal to 0. What will be the equilibrium point? Okay, Joshi, V0 by R is VC steady state, but what will be your V0 in this case? So will any current be coming from your input side? What will there be any current coming from input? I input. How
No, sir.
much?
Current and voltage will be 0.
Okay, so your I input will be equal to 0. Okay, good. So you are saying current and voltage will be 0. So this voltage also will be 0, right? So if you look at this circuit, it is just your L, C, and R. Like this is your circuit. So now this is your IL and this is your VC. If you think in steady state, what will happen? Your inductor will be shorted, your capacitor will be open circuited. That is why your voltage V0 will be equal to 0, and hence your current IL also will be equal to 0. Okay. Make sense?
Sir, IL will be there, sir.
No, IL also will become 0, right? Because this voltage becomes equal to 0, this voltage also becomes equal to 0. So there is no voltage drop across the inductor. So current will become 0. Right? So, okay, let me explain it again. So you have your inductor is over here, you have your capacitor over here, and you have your resistor over here. Okay, this switch is closed, this switch is open, this switch is open, right? So now this is your IL, this is your VC. They form sort of like a tank circuit, but they have a resistor R. It is kind of like a tank circuit and they have a resistor R. So what do you think should happen? The energy stored in the inductor will be transferred to the capacitor, and vice versa, it will be transferring, but some energy will be dissipated by your resistor R. That's why finally in steady state, your output voltage will become equal to 0. And since your output voltage becomes equal to 0, your inductor current also will become equal to 0. Okay. Yeah. Any doubts in this, or you want me to repeat again? Will you tell me which point is confusing over here?
It is clear, sir.
Okay. Okay. So these are your 2 points. Now, so let us draw. So say this is your IL. Let us know this is your V0 and this is your IL. Okay. So the equilibrium point when Q equal to 1, That means this was your equilibrium point, right? It was V in over here, and this is your V in upon R. So this was your equilibrium point when Q equal to 1. And your equilibrium point when Q equal to 0 was this, right? This was your equilibrium point when Q equal to 0. Hmm? Is that fine?
Yes, sir.
Okay. Right. Yeah. Now, what will happen is, but you want your buck converter to operate somewhere over here. Somewhere you want it to operate somewhere over here. Well, this is your V output, your rated value, let us say some 1 volt or something. And this is your current, your IL average, which you want. So this is the operating point where you want it to work. So what will happen is, it will be on like this, and it will be off like this. So this is how it would behave. Let me zoom in and show. So this is your equilibrium point when Q equal to 1, and this is your equilibrium point when Q equal to 0. But you want your buck converter to operate at this point. So what will it do? It will start from some higher value and fall to some lower value. Then when it switches off something, it will again rise, it'll again fall, again rise. Like that, it will continuously be circling around the operating point which you want. Okay, so that is how the buck converter will work. Okay. This is your current ripple, and this is your voltage ripple, which you guys have seen, right? Current ripple and voltage ripple in a buck converter, how to calculate and all. Okay. So now let us write your buck converter. It is discontinuous. Your vector field of the buck converter is discontinuous. Like in some cases, it is going down like this. In some cases, it is going up like this. So this is when it is going down. This is when it is going up. So it might start here and then it will go up like that. That depends on your time you give. If you give more time, there'll be more ripple. If you give it less time, there'll be less ripple. Right? So your time also is important. That's why sir was saying we have to carefully select the time and we have to carefully select the ripple as well. Okay. So now, sir had considered two conditions. One is a load step transient, and one is a voltage step transient. These were the two cases which sir had considered. Okay. So start. You have let's say again. Here your buck converter like this. L C R, right? This is how your current will look. In steady state, this is how your inductor current looks. And this is how your, it will go like this 1 minute. So this is your average current. This is your average current. Okay. So your capacitor current will be something like this. This will be your capacitor current. It will be like this, like this, like this, like this. So this is your I output. This is your average I output. This is your IL. This is your IC. So let me repeat it once more. So your inductor current is going like this, on, off, on, off. It is going around some average value. That average value is your I output, that is your load current. Okay. Now your capacitor current IC, it is equal to your IL minus your I0 average, or I0. That means your average value of your capacitor current will be equal to 0. So that's why your capacitor current average value is 0. Now we want to draw how your output voltage will look. Okay. So when your capacitor current is positive, that is in this region over here, that time your output voltage will rise. And when your capacitor current is negative, that time your output voltage will fall. Okay. So if you will draw the curve for that, this is the points, these are the points, right? So in this time, your capacitor voltage will rise. In this time, it will fall. Again, it will rise. Again, it will fall. Right? So again, it will rise. Again, it will fall. This is when it is falling. No, no, no. Wait, I made a mistake. So let us draw it here, 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 and here. From here to here, it is rising. Here to here, it is falling. Again, it will rise. Will rise. Here it will fall. Right? Again, it will rise and fall. Okay. This is how your output voltage will look. I have not drawn it accurately to scale, but this is how it will look. So what is important for you to understand is when your IC of T is positive, that time your output voltage will increase. Why? Because charge is flowing into your capacitor. But when your capacitor current is negative, that time your output voltage will fall because your charge is being discharged or extracted from the capacitor. Okay. So in this thing, any queries there, or you want me to repeat it again?
Yeah, it is clear, sir.
Okay. Okay. So this is your steady state operating waveforms. This is your steady state operating waveforms. Now, the two cases which suggested, your load step transient and your voltage step transient. These are the two cases which Sir has told. So what happens in that case? To draw a diagram. Let me do drawing here itself. So your load current was like this. Suppose it was like this. It suddenly changes like this. It has suddenly changed like this. That means there has been a step up for your load current. When there's such a step up in your load current, what will happen is your IC will become negative more, become more negative, and then it will slowly start coming up. And your inductor current, which is here, it will take some time. Inductor current will not change instantaneously, but your capacitor current will change instantaneously. So what will happen is your output voltage, which is here, this will dip. It will dip. And then depending on how your inductor current changes, how how this adjusts itself, because it has gone here, then it will come like this. So your output voltage also will change like this. Okay, so in that case, this is your undershoot, dV undershoot, and how much time it takes to reach steady state, that is known as your recovery time. Okay, I'll make one more diagram. This is not good. Let me draw one more diagram. So your inductor current was working like this, and this was your load current I naught. Okay, all of a sudden it goes like this. So there's a step change of your load current, that is going to be a delta I naught. Now, previously your capacitor current was going same way, only it had zero average. Its average was zero. Now, because your load current has changed instantaneously, your capacitor current, it will have a dip. It will have a dip. Okay, and then your inductor current has to rise a lot. It has to rise a lot, and then it will come back. Okay, then it will settle at this value finally. So, how your capacitor current also will go? It will also rise. It will also rise like this, and then come back, and then it will go on with the average value of 0. So now, what will happen to your output voltage in that case? In that case, your output voltage, it was somewhere over here, right? It will have a dip. As long as your current is less than 0, it will keep on dipping. Once your current crosses 0, capacitor current crosses 0, it will start rising. And then finally over here, it will settle. It will settle. So this dip is known as your delta V naught. This is your undershoot. The time it takes to settle, that is known as your recovery time. Okay. And I think this is your peak current. I have to check again. So I think this is your peak current. Okay. So any doubts in this? This is for your load transient, load step up. So load step up, what you're trying to do is, you're trying to make this Q1 equal to this total charge Q2. So it's made it Q2, Q3, etc. But you want the charge Q1 is your negative charge and your Q2 is your positive charge. Both should be equal. Both these charges, if they are equal, then your V1 over here and this V2 over here, they will be the same because the net charge is the same. Okay. And this is known as a load transient where this load current I naught that can change. That is a case when your load current I naught can change. Now, what do you think of this voltage step transient which I've written? What do you think that stands for? Anyone can tell?
Reference voltage, input voltage change.
Okay, so this is for your reference voltage. So next is reference voltage step change. Okay. So you want your output voltage. Earlier, suppose your output voltage was 1 volt. You want your output voltage 2 to become equal to 1.1 volt. So this delta Vref is equal to 0.1 volt. Okay, so you're changing your reference. You're changing your reference from 1 volt to 1.1 volt. So the step change in your reference is delta Vref, that is equal to your 0.1 volt. Okay, so how should your converter behave in that case? So what do you have is let's say over here. Your inductor current was going on like this. Okay. Now your output voltage was roughly we ignore the ripple. Let us say the ripple is very less. This was your output voltage. Now what you want to do? You want your output voltage to go to this value with some delta V ref given over here. So now what should happen? Your capacitor current should increase a bit, the inductor current will increase, and then it should fall like that. So, sorry, this would at this time it will reach. You want it to reach like this. This is your delta V. Okay, and then again your inductor current will continue further like this. This is your inductor current which has some average value. And this is your output voltage. So your output voltage should change, should go from this value to this value, right? And the time it takes, this is your recovery time. And this current, this is known as your peak current. Okay. So, we have done, okay. Let us say this your T axis, this your capacitor current. So capacitor current has this average value like this, like this, like this. Over here, it will have this peak, then fall down, again go like this, like this, like this, like this. Okay, so this is your capacitor current. where its average value is 0. But when you are increasing your voltage, this is the positive charge which is flowing, and this is the negative charge. This is your negative charge, and this is your positive charge. Okay. So let us say this is your Q positive, and these two green ones over here, they are your Q negative. So should your Q positive be equal to your Q negative? Is my question.
No, sir, because voltage has changed.
Exactly. So your delta V naught is equal to your capacitor charge into your delta Q. That is your Q positive minus Q negative. So you wanted your voltage to go from 1 volt to 1.1 volt. Okay. Let us say your capacitance is 1 millifarad. Let us say capacitance is 1 millifarad. So how much charge do I need? My delta charge Q, which I need to change my voltage, that delta Q is equal to my delta V naught by C. That is equal to 0.1 by 1 millifarad. So that is equal to how much? How many coulomb?
100.
So it is 100 coulomb. Okay. Now I want to ask a question. If your capacitor is more, would more charge be required or less charge be required?
If delta
Less.
V is constant, then for high C, value of C, delta Q will be less.
See. Okay, so C is equal to, no, let me say
Sir,
that.
one more. C into delta V should be delta Q, right?
Yeah, that's what I was confused. Yeah, that's the issue. So you have IC is equal to C dVc by dt. So your C is equal to IC into dt upon delta V. So this is equal to your delta Q by delta V. Sorry. So your delta Q is equal to C into delta V, right? So your C is 1 millifarad, delta V is 0.1 volt. The charge required, that's why is it is around 0.1 millicoulomb or 100 microcoulomb. Okay, this is your delta Q which is required. Now, suppose your capacitor is made 2 millifarad. Then how much delta Q you would require? For the same delta V naught change of 0.1 volt.
200 microcoulomb.
So you require 200 microcoulomb. Now, who will provide this charge? Where does this charge come from? This charge comes from your input. This charge comes from your current. That means the current has to now become more. Current has to become more. The peak current has to increase. Okay. So that is how your L and C have an impact on your performance. Hmm. Your L and C will determine this time and how much charge is required. And if more charge is required, more time it will take. And if you think of it in a kind of engineering perspective, if you have lots of capacitance, means your capacitor, what it does, it will resist a change in voltage. So if you have more capacitance, then you have to put more charge, you have to put more effort to change the voltage. But if your capacitance is less, then with not that much effort, with not that much charge, you can change the voltage. Okay. So the capacitor is kind of like an inertia. It's an inertia which kind of prevents or it kind of opposes a change in voltage, right? So if you want to change your output voltage quickly, fast, then you would have to have a lower value of capacitance. So this is for your capacitance and for a voltage change transient. Okay, any doubts in this, or you want me to explain anything about this?
Sir, in that IL waveform, will its average value change after that transient?
Yeah,
Because
yeah.
output voltage has changed.
Yes, the average value will change. So its average value should we go, let me use another color. Average value suppose is this. After your transient, average value will become slightly more, slightly, very less. Because your, suppose this is your I average 1, this your I average 2. Okay. So your I average 1 is equal to I average 1 is equal to your V1 upon R. And your I average 2 is equal to V2 upon R. But your delta V is like 0.1 volt. So it changes slightly, but not much. But it will change. Okay, so that also it should have been there in the waveform, not drawn properly. But it should be there. That it's good you pointed it out. I average will change slightly.
Okay.
Okay. Okay, so let us solve some sums. Let us try to understand the sums, everything. Because this is a very advanced, complicated thing. And you have been given the videos also. Like we are conducting the sessions, preponing the sessions. So probably you've not had time to go through the videos, everything. So it will be difficult. But we are doing these sessions. We will be solving the sums also, which will be helpful in solving the assignments. And then you can also go through Sir's videos and try to understand it as well. Okay. So let's switch over to the questions. So this is question 1. Okay. It's a sliding mode control. It's question 1 is regarding sliding mode control. Okay. So have you guys been able to go through the videos till now, or you were not able to go through the videos?
Not fully, sir.
Okay. What about
No, sir, only week 9 is only. Week 10 I have not seen.
Yeah, yeah. And, you submitted your week 9 assignment?
Not complete, but I'm solving that.
Okay. So this is like really going advanced actually. So usually before the exam, uh, if a professor starts teaching a subject, some topic which will not come in the exam, let us say you have your mid-sem exams, and mid-sem exam is on 10th of October, and or your professor keeps a class on 8th of October, and he teaches a topic which is not coming in your midterm exams, then the students don't pay attention. So it because it's they are so worried about the exam and everything. That's how it happens actually. So this is I think something after your week 9, so it's a bit difficult. Yeah, let's try to understand this. Okay, so you have question 1. This is your sliding mode control. Okay. So in sliding mode control, what is the objective of sliding mode control is you have some x1 and you have your x2. Okay. And there is one kind of sliding surface. This sliding surface is known as your sigma x, which in the things which we are limiting ourselves to is a linear surface. So since it is a linear, since it is linear, it can be written as a straight line, whose expression we usually write it down some k1 x1 plus x2. It is a linear expression. and this part is sigma greater than 0. This part is sigma less than 0. Okay. This is the equation of a line. This is your sliding surface or line, because we are restricting our phase to two, restricting the states to 2 as we are looking at it. So you have sigma greater than 0 here, you have sigma less than 0. Now, here you will have your u positive, here you will have your u negative. Okay. So this can be considered a case when q equal to 1 and u minus is the input when q equal to 0. Okay. U plus is when q equal to 1, that is your input is connected. U minus is when q equal to 0. What we want is that this guy's xc plus, the equilibrium point corresponding to the input q equal to 1, lies on the opposite side of sigma. And the xc minus, this should lie over here. So what happens is, if your state was here, it would be driven this side. Once it crosses this, what will happen is you will drive it this side. Then again it will be driven this side, this side, this side, like that. That is how it is being driven. Okay. So your vector field would be pointing in this side. It should be pointing this side. Here you would want it to point in this side. Okay. And there are three types of points which sir has told, three different conditions. One is if at a point one vector field is going like this, another vector field is going like this. So this is known as a refractive region. That is, from one side it is going in, from another side it is going out. And this is your sigma of x. Another case is both sides it is coming in. And this is your sigma x equal to 0. So this is known as your reflective region. And another case is both are going out. That is known as your rejective region. So there are three regions. One is refractive, where the vector field is going in through one side, and for the other side it is going out. Another case is your reflective region, where your vector field is going in both directions. Another case is you have a rejective region where your vector field is going out in both the directions. Okay, both the directions are there. So in a general sense, what would happen is, when your sigma is less than 0, your input will be q equal to 1. And when your sigma is greater than 0, your input will be q equal to 0. And when your input is q equal to 0, what it will do is it will try to come to this side. Okay. And when your input is q equal to 1, it will try to come to this side. So your objective is what? You want it to be on this line. You want your trajectory to go in this line. And since if it goes here, it turns off, turns on, it will keep on going like this. So this is known as a chattering. This is a problem called chattering, which happens in sliding mode control. And that problem of chattering you can mitigate by considering some hysteresis band and other things. Those are there. Okay. So this is a concept of sliding mode control. And it is known as a variable structure control. Why it is a variable structure control? Because at one time q equal to 1, after some time q equal to 0. So the structure is being changed. So that's why it is a variable structure control. And what you are trying to do is, you're trying to restrict the motion of your trajectory within one line. So it is actually a second order system, right? But you want it to behave like a first order system. So you're reducing the dynamics. And sliding mode control, like once it comes within this line, once it comes within this sliding surface, what happens is, since it its operation becomes almost independent of your input, almost independent of your input. So that is a very good, what you say, very good feature. That is, it is doesn't depend much on your input or your control input. So that is a feature of sliding mode control. And now, if your point is over here, you want your point to go this side, but what if it's going this side or further away, that you don't want it to happen? So there is a condition known as your reaching condition, that is given by sigma into sigma dot should be less than 0. That's Sir's derived. So that is known as your reaching condition. Okay. So it's a variable structure control. You're trying to reduce the dynamics. If there's a reaching condition given by sigma into sigma dot should be less than 0. And it has very less dependence on your input voltage or on your control input. Okay. So that's what the question is about here. Sliding mode control has less dependence on your control input. Its reaching condition is given by sigma into sigma dot is less than 0. Is the switching law continuous or is your switching law discontinuous in steady state?
Discontinuous.
Yeah, it is discontinuous. Okay, so this is false. And the next thing is, it is a variable structure control with a discontinuous vector field is true. Okay. So only your statement 3 is false over here. Okay, so I'll proceed to the next question. Okay, so we have to find the equilibrium points for this system. Let us do So we have question 2, where we have to find the equilibrium point. Your x1 dot is given by 3x2 minus 5x1 plus u, 3x2 minus 5x1 plus u, and x2 dot is equal to x1. Okay. So what are the equilibrium points? Equilibrium point is a point where your derivatives are 0. That is, your x1 dot should be equal to 0 and your x2 dot is equal to 0. You get two conditions you get. So if your x1 dot is equal to 0, what does it mean? Your 3x2 minus 5x1 plus u is equal to 0 and your x1 is equal to 0. Okay, x1 is equal to 0, very good. So you get your 3x2 plus u equal to 0. So your x2 is equal to minus u upon 3. Okay. So your equilibrium point, that is your x1 equilibrium and your x2 equilibrium, is given by 0, minus u by 3. So these are your equilibrium points for this system. Now we are talking about sliding mode control, where your u has a u plus and a u minus. So what is your u plus given by? Your u plus is 1 and your u minus is minus 1. So this is your 1 and this is your minus 1. So your xe plus is given by 0 minus 1 by 3 and your xe minus is actually 0, 1 by 3. Okay. Your xe plus is 0, minus 1 by 3. Xe minus is 0, 1 by 3. So these are your two equilibrium points. So this is your state space plane x1, x2. This is your sliding surface. Where will your xe plus come? In which quadrant?
Negative y-axis.
It is 0, no? So it is so it will be negative y-axis. So this is your 0 comma minus 1 by 3. This is your xe plus. This is your xe minus 0 comma 1 by 3. Okay. Good. So over here it will be your u plus, over here it will be u minus. There is one stability that once it has reached this surface, it will be chattering like this, right? So will this chattering go towards the origin, or will this chattering go away from the origin? If it goes toward the origin means, if it is goes towards origin, it means it is stable. Okay, but if it goes away from the origin, it means it is unstable. So now we want to find the stability property once it is on this surface, whether it will be going toward the origin or it will be going away from the origin. So for that, we will consider what is our sigma x. The sigma x which we have defined over here, that is equal to px1 plus x2. Okay, it is px1 plus x2. Okay, this is your sigma x. Now if you look at it, what is your x2 dot is x1, right? X2 dot is equal to x1. What you can write your x1, you can write it as x2 dot. So what you do, you write this is px2 dot plus x2. This is your sigma x. Now, when it is on this surface, when it is on this line, that time what happens? Your sigma x is equal to 0. So if your sigma x is equal to 0, that means your px2 dot plus x2 should be equal to 0. That means your px2 dot is equal to minus x2, right? What will be the solution of this equation?
X2 0 into e raised to minus 1 by p into t2 t.
Is e raised to minus 1 by p into t into x2 0, right?
Yes, sir.
Yeah. That means your x2t, let me write it neatly. I don't know how you guys tolerate my handwriting. E raised to minus t upon p into x2 0. So that where will it settle? So when time t tends to infinity, what will be your x2 infinity?
If p is positive, then it will go to 0.
Okay. So it depends on condition. So if p is greater than 0, this will go to 0. If p is less than 0, what will be your x2 infinity?
Infinity.
Yes. Right? So your p determines your stability. That means this is your sigma x, which is equal to p x2 plus x1 or something. No, sorry, px1 px1 plus x2. So this is sort of like the slope. P is sort of like the slope. So your slope of your sliding surface determines your stability. So this also you have to keep in mind. Okay, any doubts in this? You want me to repeat it or anything? Or I can proceed. Okay, I think I'll take the liberty of proceeding. So,
Sir, is that actually the slope P or
it is somewhat related to the slope. So let us say what is your equation of straight line? Equation of straight line is y equal to mx plus c. Here c equal to 0. So your y is equal to mx. In our case, our sigma x is equal to p into x1 plus x2. So your x2 is equal to minus px1, right? So your slope m is equal to minus p. Yeah. Slope, yeah. Slope m is equal to minus p, yes.
the negative of the slope?
Yeah. It's a negative of the slope. Correct. Okay. So if you change your p, the slope of your line will change. And that's
Okay.
what designing. And that's what you are deciding. Hmm. Okay. Let's go to the next question. Question 3, load transient optimal control. So let us say V in is 5 volt, Vref is 3.3 volt, L is 2 microhenry, C is 100 microfarad. Okay. So question 3 is for a load transient. Step up. You have your input is 5 volt. V out is 3.3 volt. L is 2 microhenry. C is 100 microfarad. And your change in step delta I naught is 1 ampere. So this is regarding the case, this case which we consider. Your load step up. Right? So for this, you have some formulas for I peak, for your recovery time, and for your voltage undershoot, delta V naught. Okay. So let us write the formula. You have to compute those formulas. You have to remember those formulas by heart. Because I don't think you will get time in the exam to derive it. So your I peak is given by square root of D into I naught. Your recovery time is given by L into delta I naught by V naught into square root of D upon 1 minus square root of D, and your voltage undershoot delta V naught is given by L into delta I naught by 2C V naught into D upon 1 minus D. Okay. These are the values. So first you have to calculate your D. How will you calculate your D? What is the value of D?
V out by V in 3.3 by 5.
Okay. So how much is that?
0.66.
Okay, correct. It is 0.66. So what is your I peak then?
Sir, is it I naught into root of d or delta I naught?
Delta I naught, sorry. Delta I naught, sorry. That is root 0.66 into 1. So Joshi is saying it is 0.82.
0.812.
Okay. 1 minute. Okay, 0.812. Yes, correct. 0.812. Okay. For recovery time, TR, how will you get it?
.62 microsecond.
2.62 microsecond. What about others? We can get a second opinion.
Yes, sir. 2.63.
Okay, very good. Now, what about delta V naught? How much is it?
.88 millivolt.
Okay, 5.88 millivolt. Okay. What about Joshi? How much did you get delta V naught to be?
Yes, sir. 5.8.
5.88. Okay, okay, yes, yes. Even Joshi is getting the same. Okay, so very good. So you guys have calculated this. So you can try remembering these formulas, or they may be also provided as a hint. So very, very difficult things, formulas where you're supposed, where it might be difficult for you to remember. Usually hints are provided. So you see the question, you see if the hint is there. If the hint is there, the formula will be there. And then you carefully substitute the values in the formula and get the answer. Okay. So in most difficult questions, you should check the hint. Check the hint if it's there. Like, try as much as possible to study the question carefully, see what exactly they want. Try to recollect from which topic, etc. it is there. See whether hint is provided. And if you're not able to get any idea about it, you leave that question. Go to the next question. And then after solving all the other questions, you come back to the question. Okay. Right. So let's go to question 4. Now, if this voltage undershoot is fixed, so what this question is saying is, question 4. Question 4 is, this delta V naught is fixed. We don't want our voltage undershoot to become more than this delta V naught. Okay, so assume this delta V naught, we fix this value. What will happen is your delta I naught, assume delta I naught can change. So what is your delta V naught? It is L upon 2C delta I naught into V naught into D upon 1 minus D. So for a normal case, what do your LNC will be fixed? LNC cannot change, right? LNC by design it is some fixed value. Your V naught also will be fixed because it is your reference voltage. You want your reference voltage to be only 3.3 volt, right? So now what can be adjusted now? Only your duty can change. So you tell me if your delta V naught is fixed, but your delta I naught can change, what should happen to your duty? Should D increase or should D reduce? So let us assume your delta I naught increases. So should your D increase or should your D reduce? As per this equation.
D reduce.
D will decrease. Correct. Because if your D will decrease, is fine. 1 minus D also will reduce. If D reduces, 1 minus D also will reduce. If D reduces, 1 minus D increases. And if 1 minus D increases, okay, D, this entire thing reduces. Okay. Correct. You could also just plot it and check once. And demonstrate it. Let us just check this formula. So D can go from 0 to 1. So let us say D is changing. Okay. Let's run it. So D10. D is changing. Okay. So your f function of D is given by D divided by 1 minus D. Let us check how it looks. So just give one value. Okay. Let's say n is equal to size of D. I going from 1 to n. F of D I DI DI. F of D, let's initialize it 0. So okay. So now let us put F of D from what is n comma F just for D is still coming like this. Yeah. DLC. Run this code. So my D is changed. So my D of 1 is this. D of 2 is this. D of 3 is this. Okay, fine. F D 0 0 0 0 0. Oh, F of D. The zeros of n comma 1. Let's try this. My F underscore D now. Again. Okay, it's coming correct now. So now let me make it D changes from 0 to 0.99 because otherwise it becomes infinite. So let me plot it with the one plot of D comma function of D. Okay, let us run this figure. Yeah. So as your D is increasing, your function of D also will increase. Ah. This we can observe. Let me change the range of D also. Let me change the range. Let me do from 0 to 0.8 itself. Let us not go for very high duty. Its label is your duty. Y label y axis is your function of D. This we can even add a line with line of 2. Okay, let us run it again. It is thicker. This is your duty and this is your function of D. Okay, so it is always increasing. Now, if you look at this curve, you can see that it is one point is here, another point is here, another point is here. It is not smooth because I've taken less number of data points. So I have a flexibility of increasing the number of data points. This linspace command says my minimum value, maximum value, and number of data points. So that I've taken to be 9. Let me take the number of data points to be 100. Okay. And then let me plot how it will look. Now you will see it looks smooth because the number of data points I have increased. So this is just MATLAB for you guys. So what is the thing is if your delta I naught which we told, your delta I naught is increasing. So the thing which we are concerned about is what is the D upon 1 minus D. So if your delta I naught increases, you want your duty to reduce. Okay, because if your delta I naught increases, your delta V naught increases. Sorry, but you want delta V naught to be fixed, so that's why you have to reduce your duty. Okay, I hope this is clear.
Yes, sir.
Okay. So now, sorry. Go for question 5. Well, we'll do reference transient optimal control. Just let me drink some water. So what we're doing is we're doing reference transient optimal control means this is the case. We had considered over here for this case. We're changing the output from, let us say, from 1 volt to 1.1 volt. Like this scenario. So So in our question, input voltage is 5 volt, output voltage is 3.3 volt. LNC values are fixed. So we have to consider a reference step of 0.2 volt. And we have to find the peak current and recovery time. So for this, input is 5 volt, output is 3.3 volt, L is 2 microhenry, C is 100 microfarad. Delta V step which you have to give is 0.2 volt. 0.2 volt step you want to give. Okay. So now what you will be doing is your peak current is going to be this formula root C by L into square root of 2 1 minus D V0 into delta V. The delta V ref. Okay, delta V ref. And your recovery time is going to be square root of LC into square root of 2 delta V ref upon 1 minus D into V0. So can you find these values? By substitution. Okay, Joshi, I peak is 4.73 ampere. Okay. And recovery time?
Uh, 5.97 microsecond.
Wow, 5.97 microsecond. Okay, let us get a second opinion for both the answers. Only Parvati has not answered till now. This question.
Sir, I got B. I peak 4.73.
Okay, okay. Right. Okay. So any doubts in these parts? Or no queries about this? Okay, by the way, Joshi, you're a BTech student, but you're from which college? You have not told us till now. Okay, okay. Fine, fine. So that is in which place? Bharati Vidyapita? Pune, okay, okay. Ah, Pune. Okay, fine. Alright. Okay. So these were things which were there. So in the future weeks, sir will be teaching how to implement this time optimal control. So something which I've forgotten to tell is, what is time optimal control? Okay. So like for me, or let us say for some person, if they have to travel from one city to another city, if the like if I have to travel from Mumbai, from Kharagpur to Chennai, okay, I could use flight. Now the issue with flight for me is I have to go from Kharagpur from my hostel. I have to go to Kharagpur station, train station, catch a train to Howrah station. Howrah station, I have to go to Howrah airport. Then I have to board my flight, and I have to take the flight till Chennai airport, and then go further to the house, etc. Now for there's another alternative is I can catch a train from Kharagpur that will directly take me to Chennai. Now, which is best? Which is best? How will you decide which is best? One is you can have consideration of time, okay, which will take me the shortest time. Usually, flight would take a person the shortest time. Next could be money, cost. Flight is expensive, train is cheap. That you could look into that perspective. Next, you could have a combination of time plus cost. You want to reduce your time which takes as well as your cost which you will pay. So you'll have to come up with some other method. There might be some other method. So this, my example is a bit, it has only probably one or two options only, but there could be different scenarios, right? There could be different options. So optimal means you have a specific criteria and you want to find the best case for that criteria. Okay. I'm really sorry. I'm having lots of hiccups. Okay, so we are considering what is optimal. Now the case sir is considering is time optimal. Time optimal means your load current changes like this. Your output voltage could change like this and come. And your inductor current could be like this. It could change like this, like this, like this. Finally, it will come over here. This is one case. Next case which you could have is current was like this, like this. Your voltage comes a little bit faster. So current will come a little bit faster over here. Next case is your voltage goes like this. Your current has changed like this, and comes off over here. Assume there could be, so which one is good, which one is bad? It has different criteria. What is a loss? How much is your peak, etc. But if your criteria is only time is important. You don't care how much is the cost, right? Then what you would do, you want to reach some maximum current and your voltage will dip somewhat, right? And then you want to reach it and it finally reaches the actual next steady state operating point. So your voltage would, in that case, would reach like this. Okay. In that case, this is the shortest amount of time it took for it to settle. This is the fastest time where you have gone from one operating current I output 1 to I output 2. You go from I output 1 to I output 2, you have many options. You have many ways you can go. But time optimal means, what does time optimal means? You want to go on the fastest time. This is the fastest time. And what they have found out is you should have one on, okay, and one off. This is sufficient. That is, your switch is turned on for some time and your switch is turned off for some time, and you can reach your next operating point. Whereas if you consider all these cases, it is turned on, turned off, turned on, turned off, turned off, turned on, turned off. It is turned on, turned off so many times. Okay. But time optimal says is, I want to turn it on and I'll turn it on for some specific amount of time where it will reach some specific value, such that if I turn off the switch, it would come back and settle at my next operating point. So that is the concept of time optimal control. Okay. So for that's why you are calculating what is this peak current. Because this peak current is a unique value that it has to go from this point to this point and then here. Now, by chance, it went to some value here. Then it would come further and again it would go somewhat and further. So it will take a little more time to settle. So that is no longer optimal. That is no longer optimal. So your time optimal is you have your fixed recovery time, you have your fixed peak current, and you have your fixed this is known as your voltage undershoot. Okay. So this is your fixed thing. Like these calculations are unique. Unique. That is what is the concept of time optimal control. So this was for your load transient case. This is for a load transient case, which I had shown earlier. Okay. Which you have done this question 4 and question 5. This is for this time optimal control. Okay. This is a advanced concept. If you have any doubts, please ask. Please feel free to ask. No doubts in this?
It is clear, sir.
Okay. So this is the case for time optimal. Now there can be different criteria that there is what you say, this current is too large. Then what they do, they keep a peak. Beyond that, it cannot go. So your current will come like this, it'll fall, it'll go like this. Something like that. So there are certain constraints also which practically you have to add. So all these things I will be teaching in your upcoming, like you guys have to go through week 10 and then in week 11 and week 12, all these details will be added. How do you actually implement it? How do you make sure that it is turned off at only at this eye peak and not further away? Something like that. Okay, so all these things sir will show. So this is for your load transient. Let me do for your reference transient also. Just say you have your voltage like this over here. Your voltage has to go to this point, right? This is your voltage. Your current was going like this. Now your current has to increase and it will settle at some other average value. As Arun had correctly pointed out, this is your I out, I average 1. This will be your I average 2. This is equal to your V output 2 by R, where this is your V output 2, and this is your V output 1, and your I average 1 is V output 1 by R. Okay. So again, you have one on, one off, and that is possible. they have implemented it, everything. Okay. So in normal operation over here, you will have a time period T. But over here, this duration is not T. Okay, this duration is no longer T. It is a little bit more than that, somewhat more. It depends on how much is your change, how much is your delta V naught, right? Etc. That can change. Okay, but that's what I wanted to point out, that this time, that this is not, this is known as your recovery time. This recovery time may be little, maybe more than your time period as well. In most cases, it would be more than your time period, because you have to, what you are doing is you are pumping in charge, right? And you're, you want to, and here what you will do is your charge which flows into your capacitor should be more than your charge which is discharged from your capacitor, right? Then your voltage, there'll be a voltage increase, step voltage will increase. Okay. So all these things are basically you're charging the capacitor or discharging the capacitor. That's why sir used to, in the derivations which sir will teach in the videos, capacitor current is a very important thing, that they are analyzing the capacitor current. They are analyzing how much time the capacitor current is effectively charging your capacitor, or how much time your capacitor current is discharging your output capacitor. Based on that, they're saying what is the change in your voltages, everything. So that is what is done for analyzing how much time you need, how much will be this recovery time, how much should be this step change, how much would be your peak current. All that they are getting those dynamics by considering the capacitor current, because your capacitor current is what is controlling your voltage, based on your capacitor current, right? Okay. So any further queries you guys have, or any interesting observations or any questions you could ask? Okay, let's try something. So we have your DIL dt and dVc by dt. Let's draw the state space of this. That is equal to your 0 minus 1 by L. And this is your 1 by C minus 1 upon RC IL VC plus Q by L 0 into Vn. Okay. This is your state space. So now let us write it down in MATLAB. Let us do your buck converter. State space representation. We consider case V in is 5, which we were seeing. V out is reference voltage is 3.3, right? Your L was 2 microhenry. Your output capacitor was 100 microfarad. Okay. So now, what is your A1 matrix? A1 matrix is 0 minus 1 by L. 1 by C out minus 1 upon R. Now R is important. Let's say R is 1. Okay. Minus 1 upon R into C out. This is your A1. your A0 also is equal to A1 because this is a buck converter. Now, your B1 is equal to 1 by L. This is when Q equal to 1. And your B0 is equal to 0, 0 when your Q is equal to 0. Okay, so you got your A1, you got your A0, B1 and B0. Now, let us find our XE1 when your switch is on. That is equal to your minus of inverse of A1 into B1 into your V in. Okay, let us find this value. So that comes equal to 5 and 5. Because your V in is 5 volt, load resistance is 1 ohm. That is why as you had told, it would settle at 5 and 5 by 1, that is 5. This is your XE equilibrium point. Right? Similarly, your XE underscore 0 is minus of inverse of A0 into B0 into B in, which will come out to be 0 and 0. Okay. So this is how you find the equilibrium points. Also, you can find it through matrix computation as well. About the equilibrium point. Okay. So now you have your A and B matrices for the buck converter. Let us just try to find what is the eigenvalue of A1. Let us find the eigenvalue of A1. Can you see the eigenvalue of A1?
Yes,
Is it
sir.
okay? So is this stable or unstable?
Real part is negative, so it is stable.
Okay. So this equilibrium point, what type of equilibrium point is? Is it a stable node? Is it a stable focus? What is it?
Stable focus.
It is a stable focus. Similarly, this should be 0 actually. And A1 and A0 both are stable focus. So the vector field for a stable focus, let us draw that vector field only. You draw it. Score for vector field. Vector field code given here. Okay. So instead of this A, let me put here buck converter matrix. A0, A1 both are same. Okay. X0, let us say from 5, 5. Okay, let us run this. Okay, it's actually the limits are not placed. Let me change the limits to minus 50, 30, 30. It wouldn't be so much, but 0 to 1e minus 3 times 1. Okay. Okay. Mm. So this is how your inductor current changes. This is how your output voltage changes. Hmm. This is how your inductor current is changing, how your output voltage is changing. Okay. And this is your vector field. This is how your phase portrait looks. So this is how it is a stable focus. Okay, and this is a stable focus. And if you draw the plot, this quiver plot, it will look like this. This is how it is changing. It is finally converging to 0. This is quiver field is not proper. It should have been x1 should have been to minus 30. X1 be minus 30 plus t. Let me run this again. Ah, was it all? I'll run it. Like this. So it is going from this point, just going on, coming here, again reducing, reducing, reducing. And these arrows point in a direction of the vector field. So is the vector field clockwise or anti-clockwise?
Anti-clockwise.
This is anti-clockwise. Okay. So that's how it behaves. Like that's how it would behave, and it will converge slowly, slowly, slowly. It will converge. Finally, it will settle. It will finally settle to the origin. Because here we are not considering any input. That's why it is finally settling there. Okay. Right. Yeah. This is the plot. So this is, you guys have seen, right? So in your steady state, in your steady state, why don't we see that behavior which we just now saw? Why don't we see that behavior? We saw that it was oscillatory, right? Why don't we see this behavior when we normally operate a buck converter?
Under steady state, that e raised to minus lambda t, those terms will disappear.
Uh, Not exactly. Like in steady state, like suppose this is how it will behave, right? In steady state, buck converter, we are only operating from this point to this point. And then your switch is turned off, so it will turn like this. Then again your switch is turned on, it turns on like this. Then turns off. So you're only doing that very small duration. So you're not allowing your system to behave at the system's natural frequency. You're making the system behave much faster, right? It is turned on, turned off, turned on, turned off. That is why these switch mode power converters you can implement a sliding mode control very easily because you can turn on, turn off, turn on, turn off. It is actually a normal way of operation is just turn on and turn off. Okay. So in normal case, what you do, you turn it on for some time, turning it off for some time. So you're not allowing it to actually go and settle in its place like the stable focus. You don't allow it. You don't give it the time. You just don't permit it to do that. So it will settle at some intermediate value. Okay, so the average of it will settle at some intermediate value. Hmm. Okay.
Okay,
That's
sir.
yeah. So any other queries or doubts, or we can end today's session? You are able to get your assignments, everything, right?
Week 9, tomorrow is the deadline. Week 10, we have. I have not seen the videos yet.
Yeah. Fine, fine. Okay. Okay, then we'll end the session. Okay. Thank you for joining.
Thank you, sir.